was mechanical turbulence, so basically the sort of stuff that you might encounter when you're coming into land. So first type of mechanical turbulence we're all kind of used to. If we look at rivers, we look at streams and we see the water flowing over rocks and we see the turbulence behind the outcrops and the rocks and so on and so forth, and we can imagine how that relates to the air. So this is, obviously when we're coming into land, we're trying not to pick landing in the lee of an obstacle, the house, the trees or whatever. And if we end up in that situation due to bad planning, then we want to try and imagine where's the least amount of turbulence going to be, make sure we've got our feet down and, pray to the gods, and hopefully we'll all land and then it'll be good. So we understand mechanical turbulence. If we look at a stream, there's something that you should observe, which is that the turbulence in its very nature is not stationary, it's moving about. And in fact, it's a great example of chaos theory, because you cannot predict what it's going to do. Okay, so if you were to sit there and go, where's it going to go next, and predict where's it going to be in 5 seconds, you're going to be wrong. Okay, so generally what we see downstream of an obstacle is we see an area where turbulence might occur. Okay, now at any particular point there may or may not be a bit of turbulence there, but over time, if you're looking at a stream long enough, you'll see the white water will move around, won't it? Yeah. Everybody nodding? Everybody's nodding on the video, good. Okay, so you've all seen it. So the point being is that there's an area where there might be turbulence. You might be really lucky. It might be your lucky day. You might just step into the bit when the smooth bit appears and great, and then after you've landed it all goes again. But generally what we do is we just go, we're imagining that in our mind, and we just avoid those bits when we're choosing where to land. Okay, it's really simple. But for some reason, when it comes to cliffs, we ignore all that, okay? And so what I wanted to talk about today was what happens at the top of a cliff. So I'm going to make a cliff. Okay, so here's a typical cliff, and here's our sea. The sea is coming in, and the air is blowing in, and it's beautifully perpendicular. It's perfect conditions for the cliff. It's obviously some days it's over here, some days it's over here, but for this day it's bang on the cliff. And so the air is blowing at the cliff, and the air out here we're going to assume is beautifully laminar. And we all go and fly around with our hands off, drinking cups of tea and whatever else, reading the newspaper, because there's nothing to do, because it's just totally laminar. But what happens to the air when it hits the cliff? Well, obviously it has to go up. And so it goes up over the cliff. And what we end up with is a lift band. Hooray! So that keeps us in the air. But what we end up behind here, just at the top of the cliff, is turbulence, or rotor, or whatever you want to call it. So, conveniently, this will represent the turbulence. And the thing to remember is it's exactly the same as downstream of an obstacle in a river, is it's not stationary. Even if the air is coming in laminar from the sea, this is moving about, okay? And we know this. We know this because quite often we take off here, okay? And we take off and we know we're taking off in rotor. And we sit there and we've got our glider out, and the glider gets blown towards us, and if we wait for the moment when the wind is filling the sail, and we pop it up, and off we go. But we know effectively it's changing, even though the air is laminar. So none of this is kind of new to anybody. This is what we've observed, yeah? But what we also know is that on a hill is we get compression. Yeah, so the air speeds up as it goes over the obstacle, we get squashed, we get the Venturi effect, so the air speeds up. So what happens is exactly the same thing happens on a cliff. The air is being pushed up, and over the top here, over the top of this mess, is the compression. Okay, and so the compression is where the air is faster than it is out here. And again, we know this, because if we pop our wing up, quite often we can't go forwards. you know, and you'll see people pushing people off, and once they get out here, they fly away. But over here, they can't, you know, all their weight's on the wing, and they can't make the thing go forwards, yeah? So again, I'm just showing you that what I'm saying, you know, we observe in our behaviour. So, why do we try and land here? That's the question. And now, the great thing about flying is that we all get to make, you know, well, the thing I think was great about flying is that we get to decide everything for ourselves, okay? So you get to decide where to fly, you choose your wing, you choose your harness, you probably, you know, you're all test pilots, because basically there's probably no one else in the world who's flying that wing with that harness at your weight.
With safety lines.
Yeah, and essentially, you know, similarly, no one else is flying at that particular specific site, at that specific position, you know, and again, the winds and everything's changing all the time. So you're making these decisions for yourself. So all I want to do is give you some information that will make you choose, hopefully, make a good choice as to where to land, okay? So, given this picture, can you make the machine go? What I did is I'm going to show some computational fluid dynamics. So we had an accident a little while back, and it made me rethink flying at cliffs. Okay, and I thought, you know, why did we have this accident? Why did this poor person have this accident? And I don't know whether this was a factor or not in the accident, because I wasn't there, and you know, whatever. But basically, what I would do is if you can zoom in on the top one for us.
Yeah.
So Robin can be the driver of this, so you can zoom straight in. So what I did is I started off and I thought, right, hang on a minute. We've flown, you know, I've flown at cliffs loads of times, many places, you know, so examples of sites where we take off and land at the top of a cliff are in this area, you know, Barton, Ypres, Southbourne, yeah, so it's like a common thing we do, okay? And because it's a common thing we do, I think what we've done is we've normalised out the risk. Because we've done it so often, we tend not to think, what are we doing? And like, when we have an accident, it makes us kind of reconsider, what are we doing, okay? So, what I did is I did some computational fluid dynamics. So computational fluid dynamics, for those who don't know, is how people try and model the movement of fluids. It's what gets used for the weather, forecasting. It's what gets used, you know, by the designers of our wings when they're trying to work out the airflow over our wings and so on and so forth. And all I've done is I've applied it to a cliff. Right, so these are fairly shitty pictures, and the reason they're fairly shitty pictures is because I didn't pay for the software. I used the trial version, and it doesn't let you save the results, so I took a picture of your phone. But what I want you to realise is that what I've done is when you run a simulation in this, it's effectively the computational fluid dynamics is it breaks everything into little tiny squares. Here I've made the squares that I'm doing the computation over about 0.3 of a metre, so 3 of them in a metre. Okay, so it's fairly small. Then you visualise it. Then you run. So basically, what it does is it runs through all these squares and it works out what's happening with its neighbours, and it works out the force, you know, and the direction of the flow, and then it increments time by a tiny amount, and then goes through again. So over time, you're basically building up a picture of what's happening, and you can watch it almost as a video. Unfortunately, if you pay for the software license. But what I've done here is I've taken a snapshot. But again, this is like taking a picture of a river with turbulence in it. Yeah, so it's just a snapshot of the turbulence, but you know it's moving about. And what you do when you see this video is you can see this moving about. So what I don't want you to do is just sort of take from this and do some measurements and go, oh, this is perfect, because it's not, because this, even when you watch the simulations, it bounces about, yeah? It moves about, nothing stays the same, because that's the nature of chaos and turbulence. Okay, so what I'm going to try and describe here with this picture is, what are you seeing? So, the bottom bit is the profile of a cliff. Okay, so we've got the sea over here, we've got a slope that comes up, we've got a bit of a flat area, and then we've got a gentle slope that goes up, and eventually we've got a vertical bit at the top, okay? And then we've got a flat bit, and that's where we tend to take off. And then we've got a house, to give you some scale, behind the cliff, okay? And each of these little arrows, on this particular colouring, it's not the best colouring for seeing the arrows, but each of these, the length of it is obviously the strength of the vector, the direction is the direction of the vector, okay? And each of these arrows, it's not drawn every square, it's only drawn every, 5 squares or whatever. So this, this is representative, the model is denser than the squares show, okay, if that makes sense. So what we're seeing here is I've just, I've provided a prevailing breeze of 5 meters per second. So 5 meters per second, 1 meter per second is 3.6 kilometers an hour, 5 meters per second is roughly 15 kilometers an hour, 16 kilometers an hour, it's roughly 10 miles an hour. Okay, so it's 10 miles an hour. 10 mile an hour breeze. And then what I've done is I've coloured this in such that I've asked it to only show me the vertical component, and I only want it to show me a vertical component that's more than 1.2 meters per second. So basically, this is the lift band. Yeah. So and the reason I wanted to do this is just a sanity check. Is the lift band where I would expect it? And hopefully it is. Yeah, it makes sense. It's kind of in front of the cliff. It extends out, and because I've just taken a picture of this off the computer with my phone, it actually extends out a bit further, but the colours are a bit more subtle. So this is kind of interesting. It shows the model is kind of correct. And we'll get on to the more interesting bits in a second. But if you scroll down, what I've also done is I've doubled the airspeed. So here I doubled the airspeed, so now we're up to 20 mile an hour breeze. And what happens? Oh, the lift band gets bigger. Okay, so it's kind of sanity check, yeah? So I think the model is a good model. So let's have a look at the interesting bit, which is the bit at the top of the cliff. So if we go on to the next one, then the colours get a little bit easier to see. Okay, so what you can start seeing now is I'm looking at the horizontal speed here, okay? So the horizontal speed, so if you remember it's 5 meters per second out here, so it's kind of like that yellow area, okay? And so where it gets bluey, it's less than 5 meters per second, and where it gets red, it's faster. So what you can see out here, yeah, nice and yellow, 5 meters per second, then we're into the compression. Yeah? Kind of what you'd expect. You've got a bit of a stagnation down here, and then here, this is our turbulence, this is our rotor. Okay, so this is the area where we're taking off, and it's also the area where sometimes we're choosing to land. Okay, now for scale, that house, that square over there where it says license, is about 10 meters high. Okay, so it gives you an idea of scale. Now for scale for us, we're interested in what our wing is flying in. Now our wing, when we're kind of standing up, is about 7 meters in the air. Okay, so it's a bit lower than that house. Now, when I saw this, what I thought I was going to be interested in was all the swirly mass that was here. So what you're getting in there, if you can have the document or whatever, you can see it, but you can see like the arrows are going backwards and they're doing what we expect, they're rotor, okay? So it's rotoring there. But the bit that I hadn't thought about...
Is that bit below the cliff the same with the airflow? Is it kind of going backwards and stuff in there?
Yeah, you get a little bit of stagnation there. Yeah.
And the same rotary stuff as well?
Yes, it is kind of, you get some rotary stuff, but what's more interesting is, and this is the bit that I hadn't thought about until I did this, is the transition between this bit and this bit. You see it's kind of like a gentle gradient. What the hell's going on up here? So basically, the problem is that we're used to thinking of turbulence as what's going on behind an obstacle, in the river, and picturing that. What's going on at the top of the cliff is we actually have got the compression, the worst bit, the strongest bit of air, the fastest bit of air, directly above the turbulence. So what we actually are doing is when we enter it, is we're not entering turbulence, we're going through a wind shear. And we're going through a wind shear where we're going, so, you know, just to give you a scale, so we look at, if you look at this, so it's 5 meters per second out here. This compression in this model is 8 meters per second, so it's 60% faster, or, you know, 2/3 faster. Yeah? So there's a high chance that, you know, when the wind picks up and you're out in front and you're doing, you know, it's 20 mile an hour and you can, you know, you can penetrate, you go back into this, it's going to be, you know, 20 mile an hour, 30 mile an hour, 30 and a bit mile an hour, 35 mile an hour, whatever, you're going to be going backwards. And you're going to be sinking through that. You're going to be sinking through that, and you can see here, over just like, you know, a couple of meters, that wind speed is going to drop to nothing, or possibly even coming from behind you. Now, if you think about how your wing works, it generates lift because of the air that's going over it. Now, when you stop having air going over it, it's not going to generate any lift. Okay? So basically, at that point, you're going to fall to the ground. Or if half of your wing is into that air, you're going to spin. Or, you know, it's not going to be good. Okay?
Can I butt in just for 2 seconds?
Yes, of course, yeah.
What Colin is absolutely saying is absolutely true, because it absolutely happened to me 3 weeks ago. So as I came in at EAP, I was judging, I was expecting the turbulence, the potential for rotor, etc. I was down, I was ready, legs were out, everything was ready for it. It was my 3rd coming in session because I laid off height twice before I came in. So it wasn't a rash decision, I came in there. As I came in, I was only 8-ish, 10 feet off the floor, full frontal, everything disappears, I go to the floor. I stand up and walk away. Luck, to the greatest degree. I've set myself up in case, but there's a lot of luck involved. And I looked at it in the same way as you did. I went back to look at it, and that shear factor is so important because, as you say, I'd normalised it, I had the image of my wing, I've got the image in my mind of this air coming up from the cliff, my wing staying in that nice laminar-ish air above the turbulence, coming in, feet down, in turbulence, fold the wing, thank you very much, walk away. But as you say, it's not stable either.
It doesn't stay there.
That shear point that we can try and imagine, which I was imagining, also
It moves about.
was undoubtedly moving as well,
Yeah.
up, down, left, right, or whatever.
Yeah.
And absolutely, I didn't gauge it correctly.
Well, I think the thing is that this is the problem, is that, say, when you watch the models go, run, it's exactly like the turbulence behind the rock. You know, it's moving about, it's doing stuff. And so this bit, you know, sometimes it goes down, sometimes it goes up. So where the shear layer is, it's not like a constant factor, it moves about. And I think, you know, it would be really easy on a strong day to come in, find you're in the compression, maybe you're not able to go forwards, maybe you're going backwards, so now you're getting further, you know, higher up above the turbulence, and then when you do hit that shear layer, you're 15 feet up, and if you land on your side, land on your head, it probably ain't going to be great. You know, falling on your head from 15 feet is probably not what you want to have happen. And as I say, it's not necessarily going to be, you're not necessarily going to even encounter it, because it's, you know, here we're looking in 2 dimensions, but in 3 dimensions it might be down this side, so you might be perfectly level, but your wing might enter it your one side first before the other, yeah?
And the wind gave no feedback.
No.
Often when you're flying into air, which is starting to get a bit jubbly, you feel sort of soft patches in it, and the wing's giving you some conversation. I went from nothing. It was absolutely stable, everything was fine, small inputs, everything was okay, and then it just wasn't.
So the question, I mean, so I'm just giving you this information because you get to choose where you land. And if you're landing right at the very front of the cliff, you can probably keep your wing in the laminar flow before your feet touch the ground. If you're landing a little bit further back, chances are you're just rolling the dice. Okay, you're literally rolling the dice. And you know, when you talk to people who fly at the coast all the time, they go, "Oh yeah, people are always getting dumped." You know, people are, you know, drop the last 5 feet and land on their back, and get up and walk away and brush it off and go and do it again. And but it might not be 5 feet one day, it might be 10 feet, it might be 15 feet, and I don't know. I mean, it just, I say, like, I have normalised this out personally. You know, I'd flown at Barton quite a lot of times. When I first went there, I thought, this is nuts. Taking off in Rotor and landing in Rotor, ooh, scary. And then by the time you've done it a dozen times, you've forgotten. And you go, oh, you just come and land, you know, you don't think about it. So it comes back down to, you know, what you were saying about landing. It's just always be switched on, always thinking. And you've got a choice. You can land down here and walk back up. And if it's windy, so if you scroll down, okay, so this is the bit that I found really interesting, is that this is double the wind speed. Okay, so this is now running at 10 metres per second. So this is more like, what did I say, it was like 20 mile an hour.
Yeah.
Yeah. But what's interesting, it hasn't changed shape, has it? I kind of thought I was going to find, you know, like, whoa, you know, it's way up here because the wind's blowing harder. And like, actually, you know, in the wind range that we're talking about here, the turbulence doesn't change shape because of the wind speed. Okay? Now, a couple of things to think about. This is an idealised model of, you know, a cliff. But what do we know about cliffs? We know that they ain't the same shape all the way along. They change, you know. Also, the wind changes direction, you know. So the actual bit of cliff that you're landing behind could be, you know, even if you thought you were landing behind this, it might actually be a steeper bit. And what will change the shape of this is the shape of the thing that's in front of you. Okay. So
Or the beach huts at the bottom.
yeah, the beach huts at the top and bottom won't really have that much influence on this bit, but the height of this lip will. And yeah, but it is. But all these are factors, and like, you know, thermals coming off the beach and so on. All of it makes it a bit of a mess.
So out of interest, Colin, if the building isn't there,
How far is it?
does that change the model a little bit?
Well, basically, it will. Yeah, I mean, there is a bit of rotor that is coming round off this building, and you know, that has an impact. There will still be rotor here, whether that's there, but it will. I mean, basically, you know, in the stream, what happens is an area of turbulence, and then it turns back into laminar flow at some point. Yeah, and so I think, yeah, that building obviously. What that shows is
kind of thinking of it like Barton, you know.
Well, this is Barton, so this is.
And you've got those buildings behind, which.
Yeah. Well, this is Barton, and I mean, you know, this is a cross section of the takeoff at Barton as best I could make it, and it's. But again, you know, the area we're landing in, it's kind of irrelevant. You know, you're not going to get beyond the turbulence.
Yeah, it makes a difference to the simulation, but no, it makes no difference to our decision making. It's the same road to regardless.
Yeah.
It's how I see it.
Okay. So let's just look at the last two. So basically, what we've looked at is. I mean, this is just reinforcing if you go up to the top one over there. Yeah. Cool. So what we've looked at is we're now just looking at the magnitude of the vector, so not caring what the direction is. Okay, so previously, so the first one we were looking at the vertical thing, you know, where the lift band was. Next one we were looking at the horizontal vector. This one is just basically, I think it is actually it's the magnitude of the horizontal vector. Sorry, I apologize. But you can see here, you can see some of the stuff that's coming back. So this is actually going backwards. These are also going backwards. But what's interesting is that down here it's like very little wind. And again, we know this because we plonk our wind out, and you know, nothing happens, and you're kind of trying to get, you know, something to inflate a cell so you can put it up. You know what I mean? And it's like, but you know, once it's up, oh, you know, blimey, can't get full. Yeah. So. I mean, that's it basically. The interesting thing for me, as I say, the conclusion, or the bit that came out of this that I hadn't thought about previously was that shear layer. And, you know, you see so many incidents where people go, what happened? Why did that happen? You know, people put videos up. There was one from me, wasn't it? And it's like, you know, this bloke came in and I don't know the guy, I don't know if he's here, but, you know, he came in and whatever, and, you know, was surprised, but basically he flew into this nest. You know, he flew into the compression and then into the, you know, in the shear layer, and it's like, what do you expect? It's, you know, all bets are off at that point, isn't it? It's just like, it's just random. And unfortunately, in this mess here, you do not have the height to sort out your shit, basically, you know, so it's like, just Do you know what I mean? It's not like pilot skill and so on and so forth at this point. It is rolling a dice.
I fly my mini wing at Barton quite a lot in 20 mile an hour plus winds, and you see this all the time. Expect it now. Is as you're coming down, so transition to the top of the cliff. Don't go too far back. As you're coming down, in my mini wing, it's a lot shorter lines anyway.
5 meters, wasn't it?
So quite often you feel yourself fall out of that shear layer, and you know where you're not pinned, you're controlling your forward speed to almost zero and trying to come down. And then suddenly you'll start dropping, but you'll also suddenly go forwards as well. And sometimes you end up back in you end up back in the lift.
Yeah, and the thing to remember is that we're kind of used to stalls and so on and so forth. People recovering stalls, and it's like. If you go on SIV and you go into a stall and then you're going to let the thing come out and it's going to dive to the horizon, and you break the dive and so on and so forth. But the only reason it's diving to the horizon is because your body is falling. You know what I mean? It's like, and what we've done here is that normal, and when you do a dynamic stall, obviously you've got some momentum in your body, but here it's like, just think what's happening. It's like there's lift, and then there's no lift. So what's going to happen is you're going to fall. And whether there's enough ground clearance that the wing can start providing some, going forward and providing some lift, is going to be luck with the gods, really.
Colin,
Anyway, so
if this wasn't a profile of a cliff, but it was the row of trees at the top of Monksdown, could you model that, or would you expect it to be very different?
It's very different.
You haven't got that sharp edge.
yeah, I think the way I would look at the with Monksdown.
We know it's bad behind there. And
Yeah, well,
for similar reasons, but I was just wondering what the picture was.
Behind
But I think with Monksdown, what you've got is basically you're not going to be landing in the compression because you've gone behind the obstacle. So now it's you're in the white water behind the obstacle. So you're going to be dropping through into that white water. And as I say, the bit that's interesting about this is it's that kind of thing that's forcing this big compression. Because we want that lift band, don't we? So I would treat Monksdown is sort of halfway between this and like an obstacle.
There are a bunch of images which show it nicely. And there's some which they class as surviving man-made obstacles in water. And Monksdown would be a long way towards that. So when you've got a weir effect, and you've got, in front of Monks, yes, there's lift, but you've effectively got the event over the top, which is what the water would do behind a weir, and you just end up with that maelstrom behind it. So it's sort of like that, you say.
It would be interesting to let off a bunch of flares and video that and just watch.
I honestly thought that when I was looking into this, so there's two things that happen. I started off with big plans to do like a full 3D model of the cliff and do all this sort of stuff. But basically, I think I discovered the information I wanted to know, which was the shear layer, and I thought I don't need to go any further. But I was kind of interested in going and getting a smoke bomb or something and stick it on a stick and going and standing at the cliff and.
This guy has done a lot of testing with smoke stuff on YouTube, and the basic, because obviously everything's so individual, conclusion is the trees are more of a slowing down, not a hard no. So you don't get the same rotor. You don't get the same low pressure that actually sucks back towards the obstacle.
Because
you just get a wind shear gradient that's actually a bit softer than any hard obstacle. Any cliff, building.
Yeah, the trees at Monksdown, you can surf
it's like a strain. Yeah, perfect.
In front of them, they've got a wave.
Yeah.
And in terms of what that means for us, in my opinion, in terms of landing behind them, is that they're much less dangerous than any kind of 90-degree shear obstacle.
But still don't land behind the trees.
Yeah.
All kinds of problems.
Yeah.
Brian, did you post a video of getting dumped at Portland?
Yes.
Robin's got it.
You had one at Portland, yeah.
That was the same effect that we're talking about.
Yeah, exactly that. Yeah.
And it was funny.
The
other
I
day.
said that you got that, didn't you?
Yeah. The other day I looked at an incident report, and I don't know why I found I'm doing something on the Westwicks website, and I found there's some old incident reports, and there was like some guy who'd flown bit too far back at Southbourne or whatever, and he said, I turned, and then the wing dived, it's like, well, I don't know why it dived, and it was just clearly went through the shit, and the wing was trying to get some speed, and he hit the cliff, and it was sort of like he didn't understand what happened, and as I say, so many of these incidents, but it comes back down to it's not, it comes down to what Robin was saying. It's like, it's not big and clever to land at the top next to your car. Just play it safe. I mean, it's your decision, but hopefully you're a little bit better informed on making that decision. And personally, if there's more than sort of 10, 15 mile an hour, and I can't land right at the very front of the cliff, I'll be landing at the bottom. So, Anyway, that's it. I don't know whether it came out on your camera or not.
Very good. GoPro, stop recording.